In the previous lecture, we finished chapter 2, and we now have chapter 3, which is about Laplace transforms. In this chapter, as I said, we have Laplace transform. We have these sections. We have 7 sections. In the first section, we have only the definition of Laplace transform. In the second one, we have Laplace transform properties. Here we have 3 properties of Laplace transforms. First, we have linearity property. Second, first shifting property, and the third one is multiplication by t to the power n property. In section 3, we have Laplace transform of unit step function. In section 4, we have Laplace transform of Dirac delta function. Then we have inverse of Laplace transforms. Here we have 2 subsections: finding the inverse of Laplace transform using partial fractions, and also finding inverse of Laplace transforms using convolution theorem. In section 6, we talk about solving initial value problems and boundary value problems using Laplace transforms. And in the last section, we talk about solving system of differential equations by using Laplace transforms. We have these 7 sections in this chapter. In the first section, we have the definition of Laplace. We say the Laplace of a function f of t, we say the Laplace of f of t equals the integration, that's the integration of e to the power minus st. We fix this, multiplying by the function, by the given function, by f of t dt, where t is from 0 to infinity, to positive infinity. That means here we just change f of t here. For finding the Laplace of any function, we say it is the integration for e to the power minus st multiplying by the function from 0 to infinity. Okay, and it's denoted by capital F of s. Here, after taking this integration, we get a function of s. In the function, we have only s. Okay. Here we have an example. It's a simple example. It says if f of t to be a, find the Laplace transform of f of t. Here, we just replace f of t here by a. Then we find that integration. We say f of s, which is the Laplace of f of t, equals to the integration from 0 to infinity for e to the power minus st times f of t. What's f of t here? T is the independent variable for f of t, but s is the variable for f of s. It's just 2 different things. I'm going to do it now. Okay. Here we can get f of s by taking this integration. It's multiplying by a. Here it says if f of t to be a, then find f of s. F of s is the Laplace transform of f of t dt. After taking this integration, we get a function of s, and that's the Laplace transform of f of t. Here we say it equals to the integration. We can take this h out of the integration. Okay, from 0 to infinity, e to the power minus st dt. Now we take the integration of e to the power minus st. S is a constant here. Because we take integration with respect to t, that means s is a constant. It's the same as to say the integration of e to the power minus 2t dt. It's the same as that. Yeah. What's the integration of e to the power minus st? We must have the derivative of the exponent, and the exponent is minus st. Derivative of minus st is minus s. So you must have minus s here. and we divide by minus s. Is it? Okay. And we say it equals to minus a over s e to the power minus st. The integration of this, here we have the derivative of the exponent. We say e to the power u times u prime. Its integration is e to the power u. If we have the derivative of the exponent, it's the exponential function itself, where t is from 0 to infinity. We now replace a t by infinity, then t by 0. We replace by infinity and 0. It equals to, yes, rule. This equals minus a over s e to the power minus s times infinity. Minus s times infinity is still infinity. If you multiply any number to infinity is an infinity. Okay, s is a constant. Multiplying by infinity is still infinity. That means we get infinity here, e to the power minus infinity. Okay, because s times infinity is still infinity, minus e to the power 0. E to the power minus infinity is 1 over e to the power infinity. E is 2.71. To the power infinity is infinity. Is it? And here we say it equals to minus a over s, 1 over e to the power infinity minus 1. E to the power 0 is 1. And it equals to minus a over s times, this is 0, because any number dividing by infinity is 0, because e to the power infinity is 0, is infinity. 1 over infinity is 0. 0 minus 1. And it equals to a over s. That means the Laplace transform of a is a over s. Here, this equals to f of s. Okay, that's how we get f of s. So how about the Laplace transform of, let's say, 2? It equals to what? We say the Laplace transform of a constant is the constant dividing by s, as we found here. The Laplace transform of any constant is the constant dividing by s. So the Laplace transform of 2 is 2 over s. How about the Laplace transform of, let's say, minus 5? How about this one? This minus 5 over s. And let's take another example. The Laplace transform of pi. Pi is a constant. It's pi over s. And the Laplace transform of square root of 2. It equals square root of 2 over s. This is the Laplace transform of a constant. Okay, so the Laplace transform of a constant is the constant dividing by s. From now, we don't need to do this integration. We just say the Laplace transform of a constant is the constant dividing by 2, by s, sorry. That's all. Here we have another example. It says, find the Laplace transform of this function. The function is e to the power at. E to the power at. Here, a is a constant. To find the Laplace transform of e to the power at, we say the Laplace transform of f of t equals the integration from 0 to infinity, e to the power minus st, multiplying by the function. Here, the function is e to the power at, okay, times f of t dt. And here we have given that the function is e to the power at. We just replace f of t by the function. It equals to, from 0 to infinity, e to the power minus st times e to the power at. This is f of t dt. We just replaced f of t by the function. We now have e to the power minus st and e to the power at. Both have the same base, so you can add or subtract their exponents. It equals to the integration from 0 to infinity for e to the power minus st plus at. Is it? Can you say that? Here, 2 to the power, let's say x, 2 to the power 3 times 2 to the power 5. Can I say it is 2 to the power 3 plus 5? Yes, you can do that. And it's the same. It's e to the power minus st and e to the power at. We can add their exponents. This is dt. It equals to the integration from 0 to infinity for e to the power. Here we take t as the common and you get a minus s t dt. Is it? Here we just take here we just took t as the common between the terms on the from the exponents. Now we take the integration. We can take now the integration. Here we say the integration of e to the power u du. Here we must have the derivative of the exponent, then we can find its integration. It means we must have u prime. When we multiply by u prime, here we have 1 over u prime. It equals to 1 over u prime e to the power u. That's all. It's the same exponential function. And here we have e to the power a minus st. It equals to, here the derivative of the exponent is the derivative of a minus st with respect to t is its derivative is a minus s. That means we must have a minus s. Then we can find its integration. So we add a minus s and divide it by a minus s. We say it equals to the integration of a minus s multiplying by e to the power a minus st dt from 0 to infinity. Here we multiplied by a minus s, so we must divide by a minus s also. Okay. Now we can take the integration. The integration of e to the power a minus st multiplying by a minus s dt equals e to the power a minus st. It equals to 1 over a minus s multiplying by e to the power a minus s t from 0 to infinity. From 0 to infinity. And here we take minus as the negative sign as the common. Here we take negative sign as the common. We say it equals to 1 over a minus s e to the power minus s minus at from 0 to infinity. We now replace t by infinity, then by 0. It equals to 1 over a minus s e to the power minus infinity minus e to the power 0. We replace by infinity and by 0 also. And you get e to the power minus infinity. Yes. هل يا بها بشر معك a minus s كد ما ب s minus a. Okay, here we take a negative sign here as the common. It's a minus yes, and becomes s minus a. Okay, it's e to the power minus infinity minus e to the power 0. This is 0 and this is 1. And here we get 1 over a minus s multiplying by negative 1. Because here we get 0 minus 1, which is minus 1. It equals to 1 over s minus a. Here we multiply it by negative sign. A becomes negative and s becomes positive. So we get 1 over s minus a. That means the Laplace transform of e to the power at equals 1 over s minus a. This is the Laplace transform of a to the power at. Look, here you have 1 over a minus s. If you multiply it by negative sign, it becomes 1 over s minus a. Okay? If you have a negative sign here, we can give it to the denominator. And because minus a plus s, is it? So you get s minus a. We have, if you have 2 over 3, we can say it's minus 2 over 3. We also can say it's 2 over minus 3. We give the negative sign to the denominator. That means the Laplace transform of e to the power at is 1 over s minus a. Let's take some examples here. Let's say if you have, what's the Laplace transform of e to the power 3t? What's a here? A is the coefficient of the exponent. The coefficient of the exponent is 3. That means here we just replace a by 3. That's all. We just use that rule. We don't need to do the process again. It is 1 over s minus 3. How about the Laplace transform of e to the power minus 2t? It equals 1 over s minus 2 and becomes plus 2. Okay, this plus 2. And the Laplace transform of e to t, let's say, equals to what? 1 over s minus 1. So that's all. We just apply this rule here for finding the Laplace transform of e to the power at. We say it equals to 1 over s minus a. And that's all. Okay. Do you have any question about that? No, you don't need to find the value of s. Only finding the equation of s. Okay, a function of s. This is f of s. This is f capital of s. The result here is f capital F of s. And now we have another example. It's about a piecewise function. It says find the Laplace transform. When you see this sign, means it is Laplace transform of f of t. If f of t is this piecewise function, f of t is this piecewise function. To find the Laplace transform of this function, we say the Laplace transform of f of t equals the integration from 0 to infinity. The integration from 0 to infinity for e to the power minus st times f of t dt. We use this rule. We use this rule for finding the Laplace transform of this function. And this is a piecewise function. It's separated in some sub-functions here. F of t equals 2 when t from 0 to 5. That means the limits of the integration for this function for 2 is from 0 to 5. And the limits of the integration for 0 is from 5 to 10. And also the limits of the integration for e to the power for t is greater than 10. Here, from 0 to infinity, is divided into some sub-intervals. From 0 to 5, and from 5 to 10, and also from 10 to infinity. We have these 3 sub-intervals. Okay? Yeah, 10 to infinity. As you see, it's greater than 10. This one is greater than 10. So we say the Laplace transform of f of t equals the integration from 0 to 5 e to the power minus st times f of t. What's f of t in this interval? What's f of t in the interval from 0 to 5? It's 2. It's only 2. As you see, from 0 to 5, the function is 2 dt plus the integration from 5 to 10 for e to the power minus st, and the function f of t in this interval is 0 plus, this is dt, plus the integration from 10 to infinity e to the power minus st. What's the function of f of t in this interval from 10 to infinity? I mean t is greater than 10, which is e to the power for t dt. Here we are going to find each of the integrations. For this one, we cannot say it equals to 1 over s minus 4. Why? Because the limits of the integration is not from 0 to infinity, it's from 10 to infinity. That's why we cannot say it's equal, we cannot apply the above rule here. For the above rule is for the function if the integration from 0 to infinity, but the limits of the integration is divided into 3 parts, from 0 to 5, 5 to 10, and 10 to infinity. Now we should find each integration here. The first one is minus 2 over s e to the power minus st from 0 to 5. Is it? We must have a derivative of the exponent, which is minus s. We multiply it by minus s and dividing by minus s, we get minus 2 of s. Then plus the second one. The second one is 0. E to the power minus s. Multiplying by 0 is still 0. The integration of 0 is still 0. Okay? Integration of 0 is c, is a constant. The constant minus itself is 0. So here we get 0. Then plus the integration of e to the power minus st, e to the power 4t dt. It equals e to, let me write down first the integration from 10 to infinity for e to the power minus s minus 4t. Here we take minus as the common between minus s plus 4. Here we get minus s plus 4t. Both have the same base. And if we take a negative sign here, we get minus s minus 4t. Okay? dt. The first part, here we replace t by 5, then t by 0. If we replace t by 5, we get 2 over s minus 2 over s e to the power minus 5s minus 2 over s e to the power 0. This is for the first part. The second part is 0. And the third part, now we take its integration. The integration of the third part is plus. It becomes minus. Minus, we must have derivative of the exponent. And derivative of the exponent is minus s minus 4 in a bracket. It is 1 over s minus 4. 1 over s minus 4. E to the power minus s minus 4t from 10 to infinity. Now we replace t by infinity, then t by 0, t by 10 here. Let's first simplify this. It equals to 2 minus 2 over s. And here you get 2 over s. Okay? We can say minus 2 over s e to the power minus 5s plus 2 over s. And this one, if you replace t by infinity, you get 0. Okay, because here we get 1 over e to the power infinity, which is 0. This minus 0 minus. If we replace t by 10, we get 1 over s minus 4. 1 over s minus 4 e to the power minus s minus 4 times 10. Okay, and it's equals to sorry. Okay. Just a moment, I'm going to write down again. I'm going to write down here, okay? Minus. It's minus. Here, we replace t by infinity, then you replace t by 0. If we replace t by infinity, you get e to the power minus infinity. If you return to denominator, you get 1 over e to the power infinity, which is 1 over infinity is 0. That means if we replace t by infinity, we get 0. 0 minus. And then you replace t by 10. You replace t by 10. We get 1 over s minus 4. Here I took this negative sign as the common. 1 over s minus 4 e to the power minus s minus 4 times 10. Okay, I'm going to write down the result here. It equals to, I'm going to write down O here. Between these two terms, what's the common? 2 over 5. 2 over s, sorry. It's not 5, it's s. Between these two terms, 2 over s is the common. 2 over s. So what's left? Minus e to the power minus 5s plus 1. And here, in the second part, we have a negative sign multiplying by negative is positive, plus 1 over s minus 4 e to the power minus s minus 4 times 10. This is the result. Okay, this is the result. Do you have any questions? It's so easy. It's just taking integrations. Just you should know that each function and the limits of the integration of each function is the domain of itself. Here, the limits of the integration for 2 is from 0 to 5. For 0 is from 5 to 10, and for e to the power 40 is from 10 to infinity. As it says t greater than 10, that means from t to positive infinity. Don't you have any question? Here, ليه رشتي وانا there's a piecewise function برجع كده باش كده أبي برجع بدوسه. Let's take some examples here about what you say. If we have, let's say, f of t to be 3 minus e to the power 2t. How about this one? What's the Laplace transform for this function? We take the Laplace transform for this, and that separates. The Laplace transform for 3, you say the Laplace transform of f of t is 3 of s. We say the Laplace transform of any constant is the constant divided by s. And the Laplace transform of exponential function, the Laplace transform of an exponential function is 1 over s minus a. A is the coefficient of t, which is 2. This is the result. We now have the other rules, the rule for all type of functions. We say the Laplace transform of a is a over s, where a be any constant. The Laplace transform of t to the power n, and we have, let's say, t squared t of to any power, is n factorial dividing by s to the power n plus 1. No, look, here we say, for example, 4 factorial is 4 times 3 times 2 times 1. We are going to multiply the number up to 1. Okay, from the number up to 1. For example, 10 factorial equals, yeah, it is 10 times 9 times 8 up to 1. Vale, let's solve a type example. Okay, we multiply it. So let's take an example about the above one. If you have, let's say, the Laplace transform of t is a cubed, it equals to what? It equals 3 factorial dividing by s to the power, as you see here, s to the power n plus 1. The exponent of t is 3. We just add 1 for the exponent of 3. Here, s to the power 3 plus 1. That's all. It equals 3 factorial is 6 dividing by s to the power 4. This is the Laplace transform of t to the power 3. How about t to the power 5 or any other number, of any other exponents? We can say it is n factorial divided by s to the power n plus 1. That's all. Then e to the power at, e to the power at is 1 over s minus a. It's 1 over s minus a. We took some examples about that one. Sine at, if we have sine at, the Laplace transform of sine at is a over s squared plus a squared. Let's take an example. The Laplace transform of sine 3t equals what? Equals a is 3 here. Only recognize a. What's a here? Determine a. A is 3. We say we just apply this rule. That's it. This one. We say it's a over s squared plus a squared. It's a was 3 dividing by s squared plus a squared is 9. That's all. And for cosine, we said s over s squared plus a squared. Look, there's a similarity between sine and cosine. For sine, we say a over s squared plus a squared. But for cosine, we say s over s squared plus a squared. But there is a difference between their numerators. The numerator of sine is a, but the numerator of cosine is s. That's the difference between them. So the Laplace transform of cosine 3t, it equals to what? Equals to s dividing by s squared plus a squared, which is 9. This is the rule for cosine. And you have the rules for sine hyperbolic and cosine hyperbolic. It's similar to sine and cosine, but this sine is negative. The only difference between sine and cosine hyperbolics, sine hyperbolic and cosine hyperbolic, is only this sign. In sine and cosine, this is positive. And in sine hyperbolic and cosine hyperbolic, it is negative. That's all. So if the sign between s and a is negative, let's take an example. The Laplace transform of sine hyperbolic of 2t, it equals to what? Equals to a dividing by s squared minus 4. A here is 2. A is 2 minus 4. It's a divided by s squared minus a squared. And the Laplace transform of cosine hyperbolic of, let's say, 5t, it equals this s dividing by s squared minus 25. Look, for sine and cosine it's plus, but here it's minus. For sine hyperbolic, that's for sine and cosine hyperbolic functions. Try to memorize these. It could be. That's for hyperbolics, must be positive for hyperbolics, but for sine and cosine it could be negative. Yeah, for sine and cosine it could be negative, but for the hyperbolic ones it couldn't be negative. Even that could be negative for hyperbolics. No, it could be negative. Yeah, it's okay. We now have the properties of Laplace transform. Let's take a break for 10 minutes. We now have the Laplace transform properties. The first property of Laplace transform is linearity property. The linearity property is these two properties together. We say the Laplace transform of the sum of two functions is the Laplace transform for the first function and the Laplace transform of the second function. We take the Laplace transform for each function separately. Then, if it is addition, we add them, we add the results, and if it's subtraction, we subtract the results. And if we have a constant which is multiplied by a function, if we take its Laplace transform, we can take the constant out of the Laplace transform, then taking the Laplace transform. That means here, for the first one, if we have, let's say, sine 3t plus cosine 4t, the Laplace transform of this function is the Laplace transform for sine 3t plus the Laplace transform of cosine 4t. We take the Laplace transform for each function separately. And if we have the Laplace transform of, let's say, 3e to the power 4t, this equals to 3 Laplace transform of e to the power 4t. We take the Laplace transform for e to the power 4t, which is 1 over s minus 4. And here we have 3 also. It's 3 times 1 over s minus 4, which is 3 over s minus 4. Okay? That is, if you have a constant which is multiplied by a function, we find the Laplace transform for the function, then we multiply the constant by the results. Here we have an example. We have the sum of 3 functions. 1 plus 5e to the power 4t minus 6 sine 2t. We have the sum and subtract of 3 functions. 1 plus 5e to the power 40 minus 6 sine 2t. Here we take the Laplace transform for 1 and the Laplace transform for 5e to the power 40 and the Laplace transform of 6 sine 2t. Then we find each Laplace transform. After finding the Laplace transforms, we find the sum or subtract of the results. The Laplace transform of 1 is 1 over s. We say the Laplace transform of a constant is the constant dividing by s. And the Laplace transform of e to the power 40 here plus 5. We can write down first the constant, then e to the power 40. The Laplace transform of e to the power 40 is times 1 dividing by s minus 4 minus 6 times the Laplace transform of sine 2t. The Laplace transform of sine 2t is 2 dividing by s squared plus a squared. A here is 2, which is 4. Now find the sum of these, you'll get the result. This equals to 1 over s plus 5 over s squared minus 4 minus 12 dividing by s squared plus 4. This is the result. This is the result for that Laplace transform, and it's done here. Okay. This is done step by step. Here we take the Laplace transform for the first function, which is 1, and the Laplace transform for the second, then Laplace transform for the third one. Here we have the Laplace transform of 5e to the power 40. We can take this 5 out of the Laplace transform. We get 5 times Laplace transform of e to the power 40. And this 6 can be here. 6 times Laplace transform of sine 2t. And you say the Laplace transform of e to the power 4t is 1. The Laplace transform of e to the power 40 is 1 over s minus 4. And it's multiplied by 5. So you get 5 of s minus 4. And the Laplace transform of sine 2t is a here is 2. 2 dividing by s squared plus a squared, which is 4. And it's multiplied by -6. We get minus 12. So this is the result for that function. Okay.
So it's L of 1.
The Laplace transform of 1.
Okay. Do we have a rule for that?
Yes, it's a constant. It's the same as the Laplace transform of a. It's 1 of s.
It's 1 over s, or
It's always
1.
Sorry.
It will be 1 over s.
Yes. It's a over s, I think. Yeah, it's a over s. I confused. Yes, you should memorize them. It's a over s. And here it's 1. So the Laplace transform of 1 is 1 over s. Okay?
So it is equal to 1.
Yes. And the second property is first shifting property. We say the Laplace transform of f of t equals f of s. If the Laplace transform of f of t equals f of s, then the Laplace transform of e to the power at multiplying by f of t equals capital F of s minus a. That means here, if we have exponential function, which is multiplied by another function. If we have e, which is multiplied by f of t, we say the Laplace transform for this together, for these two functions together, is capital F of s minus a. That means here we are going to find the Laplace transform of f of t, and then replace each s by s minus a. We replace each s by s minus a. Okay. For example, the Laplace transform of e to the power 2t cosine, let's say 3t, equals to what? Here we are going to find the Laplace transform of 3t, cosine 3t. What's the Laplace transform of cosine 3t? You say this f of t. The Laplace transform of cosine 3t equals s dividing by s squared plus 9. And here a is 2. This equals to, in the Laplace transform of cosine 3t, we replace each s by s minus a. What's a here? A is 2. A is the coefficient of the exponent of e. A is this one. A equals 2. Here, you just need to determine what's f of t and what's a. What's a? A is the coefficient for the exponent of e. So if you replace each s by s minus a here, it's s minus 2 dividing by s minus 2 squared plus 9. That's all. Okay? The proof is not included for you. And for the
cosine
3t, cosine 3t is s. This is the rule. It's here above. That's it. We say cosine at is s over s squared plus a squared.
equals 2.
Sorry?
The value of a equals 2.
It's 3. We have cosine 3t. But look. for this function, this is A. The Laplace of cosine 3t is that one. Okay, but here we are going to choose this one to be A. We are going to take the coefficient of the exponent of E to be A. Okay, here we have some examples. Let's prove this one, even the proof is not included for you. To prove this, we say we need to prove that f of s minus a equals to this one. We need to prove that these two are equal if we have this. We have given that the Laplace transform, the Laplace transform of f of t equals f of s. It's given. And we must prove these two. We must prove that f of s minus a equals to the Laplace transform of e to the power at f of t. And this equals to the integration from 0 to infinity for e to the power minus st multiplying by f of t dt. Okay, how about f of s minus a? Here, f of s is e to the power minus st. How about f of s minus a? We replace each s by s minus a. That equals to the integration from 0 to infinity e to the power. We replace s here by s minus t minus s minus a, sorry, t. Just here we say f of s equals e to the power minus st f of t dt. How about f of s minus a? We replace s by s minus a times f of t dt. And this equals to the integration from 0 to infinity for e to the power minus s plus at f of t dt. This equals to the integration from 0 to infinity for e to the power minus st times e to the power at times f of t dt. We just separated the exponents. That's e to the power minus s and e to the power a. That's e to the power minus st, e to the power at. Okay, and this equals to, this is, we let this to be the function. Okay, and it's multiplied by e to the power minus st, and its integration from 0 to infinity. This is the Laplace transform of e to the power at f of t. As you see, we proved that f of s minus a equals to this one. That means if we have e to the power at, which is multiplied by a function, we first find the Laplace transform for the function, then we replace each s in the result by s minus a.
Can you just repeat the last step of that?
This one?
Yeah, that one of the.
Okay. This one, here we have e to the power, I'm going to simplify it more, minus st plus e plus at. We just give this t2. Yeah, just multiply it into the bracket and then expand. Okay, we got this.
Okay.
Okay.
Thank you.
We now have an example. We have an example. Here, what's f of t? What's f of t? F of t is this one. And e to the power at is this one. That means f of t equals t. And a is this exponent, which is 2. So we just apply the rule. First, we should find the Laplace transform for t. It's a polynomial. It's t to the power n. N here is 1. It's 1 factorial divided by s to the power 1 plus 1. We just add 1 for the exponent. We say from this, the Laplace transform, let me write down below. So the Laplace transform of t equals 1 factorial, the exponent is 1, dividing by s to the power 1, we just add 1 for the exponents. It is 1 over s squared. Now we have a equals 2, and the Laplace transform, this is f of s. How about f of s minus 2? F of s minus a here is 2. It's f of s minus 2. The Laplace transform of e to the power 2t times t equals f of s minus 2, which is f of s minus a, as we said before. This f of s minus a. We have f of s. We have f of s, which is 1 over s squared. We just replace each s by s minus 2. It equals to 1 over s minus 2 squared. This is the result. This is the Laplace transform of e to the power 2t times t.
So a question for the f of t, the rule is always a over s.
No, it's not always. Look here. It depends on the function. If the function is a polynomial, there's the rules. Here you have the rules. We say if this is a polynomial, if t to the power n, it's n factorial of s to the power n plus 1. So what if it is sine? It's a over s squared plus a squared. That's the Laplace transform for that. If f to be sine at, if f to be sine hyperbolic of at, it's that. If f to be cosine at, it's that. Okay. So it depends on the function. Here the function is t. That's why we say it is 1 factorial, the exponent factorial. You see the Laplace transform of t to the power n equals n factorial divided by s to the power n plus 1. And n here is 1. That's why we say it is 1 factorial over s to s squared, which is 1 over s squared. And then we replace each s by s minus 2, as you have e to the power 2 here, by applying the first shifting rule property. We have on the example, it says the Laplace transform of e to the power 4t times cosine t, e to the power 4t times cosine t. So let me play this. Here, f of t is, what's f of t here? Only the cosine function. Cosine t. What's a? It's 4. Here, we first should find the Laplace transform of cosine t, which is f of t. It equals to s dividing by s squared plus this coefficient squared, it's 1. Okay, the coefficient here is 1. The coefficient of the angle is 1. We say cosine 80, the Laplace transform of cosine 80 is s dividing by s squared plus a squared. Okay, here a is 1 plus 1. This is f of s. And the Laplace transform of e to the power 4t cosine t equals f of s minus 4, since a is 4. That's f of s minus a. Since a is 4, so that's it. F of s is s over s squared plus 1. That means we replace each s by s minus 4. We get s minus 4 dividing by s minus 4 squared plus 1. That's the result. This is, so the Laplace transform of e to the power 4t cosine t is that. Is that easy? It's only applying the rule. Yeah, it's only applying the rules. If you just know the rules, that's it. Okay. We have the third property, which is multiplication by t to the power n property. If you have a function which is multiplied by t to the power n, we first find the Laplace transform of f of t. Then we take nth derivative of the results with respect to s. We take the derivative of f of s with respect to s n times. If t to the power 2 means we take two derivatives. F to the power 1, we take one derivative. F to the power 5, we take 5 derivatives. Okay? Here, we say the Laplace transform of t to the power n. اگر فانکشنك ما هبه ضرب t بتواني اجمالي كلات. t بتواني 2 3 هرشنك. t بتنياش بيه بكشين. ليرة فانكشنك ما هي ضرب t بتواني اجمالي كلات. يعني كانت شيء ناقص يك بتواني n. ناقص يك بتواني ام n ام تواني. تواني تيكي. ضربي داتا شاوي اني بوچی بو لاپلاسی نقشەکە لاپلاسی نقشەکە وەرەگرین جاري نقشەیەک ما هي ac تیایە وایە لاپلاسی f of t نقشەیەک مانیاتە کە ac تیایە f of s دۆتینەوە دین چێکین ئەڵێن ئەکاتە ناقسێک بەتوانی n ضربی n داتاشا بۆ f s وەرەگرین بەنسبەت s بۆ نمونە for example if the here we have an example. There is no enough space actually to write down another example. Here we take n derivative for the function of s with respect to s. For example, if we have s over s plus s squared plus 4. The derivative for this, yes, it's only rules, nothing else. Let's see. Here we have s over s squared plus 4. The derivative of this function with respect to s, you say denominator times derivative of the numerator minus numerator times derivative of the denominator dividing by denominator squared with respect to s. Here we have an example. It says the Laplace transform of t sine 60. What's f of t and what's n? We should determine these two. F of t equals sine 60. N equals 1. First, let's find f of s. That means the Laplace transform of f of t. The Laplace transform of f of t equals the Laplace transform of sine 60. That equals a, which is 6, dividing by s squared plus a squared, which is s squared plus 36. Now, since n is 1, that means the Laplace transform of t times sine 60 equals minus 1 to the power n. N here is 1. Is it? Then we take only one derivative. This is f of s. We take only one derivative for f of s with respect to s. Why we take only one derivative? Because the power of t is 1. If the power of t is 2, we take 2 derivatives. If it's 3, we take 3 derivatives. For this one, it equals to minus 1 to the power 1 is minus. Derivative of this function with respect to s, you say denominator squared, s squared plus 36 squared. And then denominator times derivative of the numerator, which is 0, minus. Numerator, which is 6, multiplying by derivative of the denominator. أنا جير ضرب داتا شاوي سرة، لسرة بس كونستانت داتا شاوي صفر كان. ناقص سرة شاشة ضرب داتا شاوي جير بالنسبة s شيء كان. This term is 0, and this term becomes 2s. This equals to minus is 12s dividing by s squared plus 36 to the power 2. That's all. Okay, here we have negative, it becomes positive. Negative becomes positive. That's why I say it's positive. 2 times 6 is 12. S dividing by s squared plus 36 squared. Yes. 2s. Yeah. Depends near. No. Second, pinch our account. Go show here. Balam is our account. Okay? We have only one more example. Okay, to finish this section. Let's do this example also. Here we have the Laplace transform of e to the power minus t sine 2t. We have three functions. We have three functions which are multiplied. We have f of t, which is multiplied by t to the power n, and it's multiplied by e to the power at. Here, we should first determine what's f of t. F of t here is sine 2t. We are going to separate it. We are going to do it in two steps. Okay. In the first step, we take e to the power minus t and sine 2t. Okay. And then we take the result of this with t. Let's do this one. Here, what's f of t? What's f of t here? Sine 2t. What's a? A is minus 1. Let's first find the Laplace transform of sine 2t. We say the Laplace transform of sine 2t, which is f of t, is 2 over, since that's sine, it's 2 over s squared plus a squared, which is 4. Now, we have this, the function is multiplied by e to the power minus t, and here a is minus 1. We replace each, this is f of s. الان اگر هاتو نخشيك ما صار exponential function كلاب او بردم تواني exponential لك شنبو لجي هر اسك لناو Laplace transform كور ما قلتوا s ناقص او جمالي. Okay, so f of s minus a minus 1. We say, let me write down again. F of s minus a equals f of s plus 1. Is it? Minus minus becomes plus. This is the Laplace transform of e to the power minus t sine 2t. And equals to this f of s. We replace each s by s plus 1. It's 2 dividing by s plus 1 squared plus 4. And now we have t multiplied by these two functions. We take only one derivative for the results. We take only one derivative for the results. About the previous one, we have this negative sign. Yeah, it's okay. We say the Laplace transform of t times e to the power minus t sine 2t. This equals to, we found the Laplace transform for this one was 2 over s plus 1 squared plus 4. We take only one derivative for it. It is minus 1 to the power 1. And here is 1. And n is 1 because t is to the power 1. Minus 1 to the power 1 df by ds. We take one derivative for this function. Denominator squared s plus 1 squared plus 4 all squared. Then Denominator times derivative of the numerator. In the numerator, you have only a number, and it is 0. The minus numerator, which is 2, multiplying by derivative of the denominator. This term is 0. The derivative for that term is 0. And for this term is 2 s plus 1. It's 2 times s plus 1. This equals to minus, here we have a negative 1. As you see here, we have minus 1 to the power 1. It's negative. It is minus 2 times 2 is 4 times s and times 1. 4 times s, 4s minus 4. And minus 4. Dividing by s plus 1 squared plus 4 all squared. Here, we give this negative sign to these two. We get 4s plus 4 dividing by s plus 1 squared plus 4 all squared. This is the result. Okay?
Sorry, what was the main difference in this?
Yep. So it's enough for today. Do you have any question?